Let's talk about electromagnetic waves, the very fundamental waves that deliberate us a lot of information about the universe and anything that's around us. So, to start with, these electromagnetic waves are a fundamental concept in physics that describes the behavior of electromagnetic radiations, which includes visible light, radio waves, microwaves, and more. And let's talk about these electromagnetic waves in a comprehension without mathematical equations. So these electromagnetic waves, these are the type of energy that does not require a medium like air or water to travel through. They can move through empty space, and this is what makes them unique. So these waves consist of two components. One is electric field, and another is magnetic field. And these fields are actually perpendicular to each other. And the propagation is perpendicular to electric field and magnetic field plane. So these electromagnetic waves come in various forms. I mean, each with its own wavelength and frequency. This range of waves is called the electromagnetic spectrum. The electromagnetic wave spectrum includes radio waves used for broadcasting, microwaves used for cooking and communication, infrared, heat, visible light, what we see, ultraviolet can cause sunburns, X-rays used in medicine, and gamma rays. These are high energy rays used in treatment of cancers. So let's talk about the properties of these waves. Electromagnetic waves are characterized by their wavelength and frequency. Now, wavelength is the distance between the two wave peaks, and frequency is the number of waves passing a point per second. And there is an inverse relationship between wavelength and frequency. Shorter wavelengths have higher frequencies, and longer wavelengths have lower frequencies. Now, to talk about the speed of electromagnetic waves in vacuum is constant, and it's approximately 29 crore 97 lakh 92,458 meters per second, often denoted by C. Now, how electromagnetic waves are generated? Now, these electromagnetic waves are created when electric charges accelerate. Now, for example, when an electron in an atom moves from one energy level to another, it emits electromagnetic radiation. I mean, the other sources of electromagnetic waves include the oscillation of electrons in an antenna for radio waves, or the vibrations of charged particle in the atom of a hot object, right? So now let us talk about the behavior of these waves, have some brief understanding about their behavior. Now, these electromagnetic waves can exhibit different behaviors, including reflection, refraction, diffraction, and interference. Now, reflection occurs when waves bounce off a surface, like light reflecting off a mirror. Refraction happens when waves change direction as they pass from one medium like air into another medium like water. This is what makes a straw look bent in a glass of water. Now, talking about diffraction is the bending of wave as they encounter an obstacle or aperture. It is why you can hear sound around the corners, right? Now, interference occurs when two or more waves meet. I mean, when they superimpose. They can either reinforce each other, and we call it constructive interference, or they can cancel out each other, and we call it destructive interference. Now, talking about the practical applications of these electromagnetic waves, these are basically numerous. I mean, electromagnetic waves have countless practical applications in our daily lives, including radio waves for broadcasting and communications, microwaves for cooking and cell phone signals, infrared waves for remote controls and heat sensors, visible light for vision and some kind of optical communications, ultraviolet waves for sterilization and mineral detections, X-rays for medical imaging and security screening, gamma rays, right? So all of these range of frequencies have range of applications in our day-to-day lives. Now, these electromagnetic waves are a form of energy that I talked about at the beginning of this presentation. Now, certainly there is a composition of electric and magnetic fields, and these vectors are perpendicular to each other, and the propagation of electromagnetic wave is perpendicular to the plane of electric field and magnetic field, right? That's the core structure of the electromagnetic waves that we have been talking about. Now, uh, uh, we talked about the various phenomena out there of these electromagnetic waves. And all of these things that I talked about, they just talk about the wave nature of these electromagnetic waves. These electromagnetic waves, they also have the particle nature. I mean, these electromagnetic waves can behave like particles under certain circumstances. So these electromagnetic waves exhibit both wave-like and particle-like properties, a concept that's known as wave-particle duality. Although they behave as waves when propagating through space, electromagnetic waves also consist of discrete packets of energy called photons, right? So to talk about the particle nature of these photons are tiny, massless particles that carry energy and momentum. They are like the building blocks of electromagnetic radiation. The energy of a photon is directly proportional to its frequency and inversely proportional to its wavelength. As we know, the very famous equation E is equal to h nu, where h is Planck's constant. To come up with some of the examples of photons and their applications, I mean, in visible light spectrum, each color corresponds to a photon with different energies, right? So, for example, red light consists of lower energy photons. Blue light consists of higher energy photons. In case of visible light, our eyes perceive different colors due to the variation, or I should say, due to the varying energy of these photons involved in these wavelengths. The photons with even higher energies like ultraviolet and X-rays have applications, right? They have applications in medical imaging. X-rays are used for imaging bones and internal structures. I mean, cancer treatment, high energy gamma rays are used for radiation therapy. Lower energy photons, such as infrared and microwaves, are employed in the technologies that are around us. infrared sensors. They are used in night vision devices and heat detectors. Microwave ovens, they heat food by exciting the water molecules with microwaves. Radio waves, which have even lower energy photons, are utilized in. They are utilized in wireless communications. I mean, radio waves transmit information in cell phones and radios. Radar systems, these radars use radio waves for navigation, weather tracking, and military applications. The energy of each photon in these examples is determined by its frequency. And to illustrate the particle nature of electromagnetic radiation. Now, the wave particle duality in action, I mean, the photoelectric effect. The photoelectric effect is basically a classic experiment demonstrating the wave particle duality. I mean, when light composed of photons shines on a metal surface, it can eject electrons from the metal. The energy of the ejected electrons depend on the frequency of the incoming light, not its intensity. This behavior is explained by the particle nature of the photons, right? To end this literal talk on electromagnetic waves, I mean, the coexistence of waves and particle nature of these electromagnetic waves. Certainly, what actually the electromagnetic wave is, we don't know exactly, but what we know is that these electromagnetic waves, they behave like waves under certain circumstances, and they behave like particles, like some other circumstances. When talking about double slit experiment, when talking about polarization, when talking about diffraction, these electromagnetic waves certainly, their behavior, the results of these experiments can only be explained by assuming that electromagnetic waves they are waves, perfectly waves in nature. But when it comes to the experimental outcomes of photoelectric effect, Compton effect, and Planck black body radiation law, under these circumstances, the light is behaving like photons. It's made up of some massless particles having different energies. And these experimental results can be explained only by assuming that light is made up of packets of energies, and the energy of each packet is h nu, where h is the Planck's constant and nu is the frequency. So, with this, I would like to end this